All right, so we spent a lot of time on Friday going through kind of the differences between strong acids and weak acids, strong bases, weak bases, and then all of those different definitions of acids and bases that we talked about. Lewis theory, Bronsted-Lowry theory. And so, you know, all of that kind of spreads down to just kind of the basic idea of if you can have a decent understanding of Lewis theory, all of the other theories kind of fall from that because what you can understand is that in Lewis theory, you have electrons going from the base to the acid, which in turn, if hydrogen is involved, that's basically what happens in a Bronsted acid-base reaction. And if hydrogen and hydroxide are involved specifically, then that's what is involved in an Arrhenius reaction as well. So the key to it is really understanding the Lewis theory and then kind of building off from there. But today's focus is going to be piggybacking off of what we just took a quiz over. And that is, we're going to look specifically at acid and base strength through the concept of their equilibrium constants. And where we're going to spend most of our time focusing is not on the strong acids. Again, strong acids are strong because their equilibrium is so product favored that if we were to measure their equilibrium constant, we would be getting values in the millions and billions, as opposed to for most weak acids, we're in the 10 to the negative third, 10 to the negative fifth, 10 to the negative 12th kind of equilibrium constant, depending upon its strength. And so the takeaway that we really want to highlight here is that when we are discussing weak acids, the overall concentration of that weak acid is pretty universally going to be greater than the concentration of the hydronium that we get from the acid being an acid. And so if we take this equilibrium expression that we would draw out for any weak acid, keeping in mind that water is a pure liquid, and so it would not be included in the equilibrium expression, the value of Ka is always going to be the concentration of hydronium multiplied by the concentration of the conjugate base, A minus or X minus, depending upon which source that you're looking at, divided by the concentration of the weak acid itself, all at equilibrium. Now, one really important note that I want to make sure that we emphasize here is that especially for values of Ka, Kb, and pretty much every other K that we're going to talk about for the rest of this semester, we don't have to worry about memorizing those values. Those values are always going to be given to us either in the problem itself or through the use of some kind of a data table. You go into Blackboard. One of the links in Blackboard is to an appendix table. The appendices there give you the weak acid constants for a whole bunch of different acids, including a number that we'll never ever use. But we're giving them to you as a reference in case you ever came across them. And we'll see the similar kinds of things when we start talking about weak base equilibrium as well. So These values are never going to be ones that you're going to be asked to pull out of the thin air. Now, sometimes we might ask you to calculate what the constant is, but we're always going to give you a means for doing so. Very similar to what we did in the last chapter. Here are your starting concentrations. The equilibrium concentration of hydronium is this, or the pH of the solution is this. Work backwards, figure out what the value of Ka is, figure out what K is in the reaction. Now, some overall words of note here. We know, based upon what we understand about equilibrium, that the larger the value of K is, the more product favored it's going to be. Well, in terms of acid strength, that means that it's going to be stronger. And so if we look at the things that we have traditionally defined as strong acids, hydroiodic, hydrochloric acid, those Ka values are large. And like I said, do we have actual values for them? Yes. I'll say that with a slight question mark at the end. Um, they have been measured. We're gonna kind of take a little bit of measure of caution on them because the values themselves are just absolutely obscenely large. Somewhere on the scale of 10 to the ninth, 10 to the 10th, 10 to the 8th. So for all intents and purposes, we consider them to be fully, completely product. Because at that kind of an equilibrium constant, we're effectively talking about negligible amounts of unionized acid material. But we can see that as we go down here, we can see that we do have, so things like hydrocyanic acid, HCN, 4 times 10 to the negative 10th for its acidity. Formic acid, we talked about that. This is what makes ant stings actually sting. 1.8 times 10 to the negative 4th for its constant. But we can also see here things like the hexaaqua iron 3 ion, this iron 3 complex that is made in water. We see this is what causes the yellow color of iron 3 solutions. And we can see that it is, in fact, acidic. Why is it acidic? Well, we have Lewis acid-base theory to explain that. The water molecules, the oxygen lone pairs, are attaching themselves to that iron. So you've got a Lewis base in the water putting on bonds to this metal center, which is, in turn acting acidic as a result. But we can treat any of these in the same kind of way that we did in the previous chapter. We know that the smaller the value of Ka, the more reactant favored it is. And in the case of acids, that means that the acid is going to be weaker because we're getting fewer hydroniums off of it. So with that in mind, let's get into our first question for today. This is a ranking question. So 4 acids have been given here. Rank them in order from strongest on the top to weakest on the bottom. So the strongest acid would be the one that had the largest Ka. That would be the one that had the least negative exponent. So that would be HSO4 negative, followed by hydrofluoric acid, followed by hypochlorous acid, HClO, and finally hydrocyanic acid, HCN. And we all got it. Good job. So let's take a look now at bases. With bases, we make the same kinds of arguments. So we know that weak bases do not fully dissociate. In terms of the concentration, we understand that the initial concentration of the base is going to be larger than how much hydroxide comes off of it. And again, since we can exclude water from the equilibrium, since it's a pure liquid, then the equilibrium expression for the base is equal to the concentration of this conjugate acid multiplied by the concentration of the hydroxide divided by the concentration of the base. And again, just like we saw with Ka, these values do not have to be memorized. These are going to be found in data tables. But again, the setup is exactly the same, and the predicted results should be relatively predictable. The higher the value of Kb, the stronger the base, the more basic we would expect its pH to be. The lower the value of Kb, the weaker that base is, the more toward neutral or acidic we would expect its pH to be. And interesting here. Okay, so that's supposed to be a table of Kb values. Obviously, it is not. Um, but if we go into Blackboard here and we go to that appendix table, so in the appendices, once you get past all of the thermodynamic values here, you'll see here's your list of Ka values. So all of your Kas for all of these different kinds of acids, ranging from strong down to here's arsenous acid at -10, boric acid at -10, hydrocyanic at -10, peroxide here at -12. And what you can also see is that if an acid gives up more than one proton, there are different Ka values for each proton that comes off. And we'll talk about this in a little bit, but you can see that there is a trend where the value of that Ka consistently downgrades with each successive hydrogen coming off. So for arsenic acid, the Ka is relatively decent, 10 to the -3rd. Its second one is okay, 10 to the -7th. Its third one's pretty weak, 10 to the -12th. And what this will set up for us is what we can see is since each successive deprotonation has its own Ka value, what that allows us to do is it allows us to look at, well, what about this particular situation? So in the case of, you know, this second deprotonation of arsenic acid, or this second deprotonation of carbonic acid, well, what does that mean? Well, it means that if I have HCO3 minus, it has the capability of acting as an acid. But similarly, it actually has the ability to act as a base as well. Again, if we think about it from a Bronsted-Lowry standpoint, it could add an additional hydrogen and go back to being carbonic acid. So in these middle states, we have a series of amphiprotic kinds of ions that could act as acids in one situation, act as bases in another situation. And based upon their Ka values, Kb values, we can actually kind of predict how they're going to react. And so, again, we'll get to this more tomorrow, but for carbonic acid, that value being 10 to the negative 11th, this is actually going to be a really good indicator of basic behavior on the part of the bicarbonate ion, because if its acid is that weak, its base character is going to be the opposite level of strong. And so bicarbonate ion is actually a lot stronger of a base than it is as an acid. That's not to say it can't act as an acid. If we put it in the presence of a strong enough base, it'll act like an acid. But on its own, if we're just putting it into water, that's why baking soda, sodium bicarbonate, has a basic kind of pH to it. But if we keep scrolling down here, and we get past all the acids, eventually we'll get to bases as well. And so what we can see here with bases is that, yes, we have some strong bases here: calcium, strontium, barium hydroxide. But notice that the second hydroxide is actually one that we can measure with a Kb. You'll find a lot of back and forth about magnesium hydroxide in terms of its base strength. In our solubility rules, we counted it as a strong base, even though it does not have nearly the same level of Kb. It's right on the kind of the line. Usually the line's about 1. But you can see, a lot of your amines and pyridines, and they all have different values to them. And so we can literally just pull these off of any table and get exactly what it is that we're looking for to do our calculations. So before we start getting these into ice tables, let's take a look at some things we're going to focus on acidity here. And there are some structural factors and some organizational factors inside of certain molecules that are going to be better equipped to dictate whether something is acidic or base or less acidic. And so Lewis structures and some of the features inside of those Lewis structures can be used to that quantity and to that end. And so we're going to take a look at some of them. So one thing that we can pull on first, we can see that there is a trend in acidity as we go from left to right on the table. So if I'm looking at hydrides, carbon hydride or methane, it has an acidic pKa of around 50. Ammonia, NH3, which is a known base, has a pKa of around 38. Water, which we consider to be acidically neutral, has a pKa of 14. And hydrofluoric acid, HF, has a pKa of 3. So just remembering that one of the principles we learned on Friday was we talked about pH is equal to the negative log of hydronium. pKa would be equal to the negative log of the acid dissociation constant. And if we were to flip it around, if we wanted the Ka, we could take 10 to the negative pKa to do it, just like we took 10 to the negative pH to get hydronium concentration on Friday. So the P is a function. The P stands in for the function of negative log. So if I take pKa, it's the negative log of Ka. If I take pKb, it's the negative log of Kb. If I take POH, it's the negative log of hydroxide. And so with that in mind, you can see, okay, the Ka of this substance, 10 to the negative third, okay, that's a relatively strong acid compared to 10 to the negative 14th, 10 to the negative 38th, or 10 to the negative 50th. And that 10 to the negative 50th for methane there, we're looking at something that's not acidic in any kind of way and also probably not basic either. So what explains this periodic trend? And the primary explanation is electronegativity. The more electronegative the center atom is that is bonded to the hydrogen, the more acidic that substance is going to be. And we have reasonable explanation for that. If I think about hydrogen fluoride, let's try this thing. From an electronegativity standpoint, fluorine is the most electronegative atom. And so it's going to draw that electron density toward itself. So the electrons in this bond are going to migrate toward the fluorine, which makes this bond weaker. And a weaker bond is easier to break. So the more electronegativity that we have in that period, the easier it's going to be to break that bond because the electron density is already pushing itself in the direction away from the hydrogen, and it would just require less energy to break that bond as a result. And you might be saying, oh, but wait a second, oxygen and nitrogen are both really electronegative as well. And you would be correct. But the electronegativity difference is even greater still in the fluorine. And that's what's going to make that bond more acidic and easier to break still than even what's in water. Now, again, looking at this from a reactivity kind of standpoint, what is that going to look like? Well, again, the more electronegative that the element is, the more easily it can stabilize that negative charge. Carbon is not terribly electronegative, so the resulting carbon here is going to be unstable. And since it's unstable, that's going to push the equilibrium far this direction. The NH2 ion, nitrogen is capable of taking that charge, but it's not terribly comfortable with it. And so again, we're going to see that push more this direction. We know hydroxide is relatively stable, and so is hydronium. This is where we get that autoionization. So we are going to see equilibrium here, but again, we know at 10 to the negative 14th, the majority of the action is over here with water staying molecularized rather than breaking apart. This is by far the most stable of these four ions. And being the most stable, it's going to be the one that's most easily kept. And so even though the equilibrium at 10 to the negative third is still left way driven, it's still reactant favored, it's more product favored than any of the other three examples. Now, what about within a column? So we talked about going across a row, and you would see the same kinds of things in period 3 versus period 2, period 4 versus period 3, the whole smash. The halogen is going to be the most electronegative of the period, is going to be the most acidic group. But if I go down a column, so let's say I'm comparing all of the halogens, I'm going to see that the acidity and the strength of that acid is going to increase as we go down. Why is this the case? Well, we can talk about the idea of atomic radius. I want to bring in a different idea, though. If you can remember back to Chem 105, we talked about this periodic trend of atomic radius then. I want to draw your attention back to it by looking at this table of values here. So if you look and see, I just want to highlight a couple of ideas to you. Let's compare hydrogen to fluorine, hydrogen to chlorine, hydrogen to bromine, hydrogen to iodine. These are the four that we're studying there. These are their four bond energies. Why is the bond energy of each of those getting succeedingly smaller? Well, your book had said something that has to do with atomic radius. What's happening to the atomic radius as we go from fluorine to bromine to iodine and so on? Yeah, they're all getting larger. We're adding more energy levels. Well, what does that do to the length of the bond? Remember, bond distance is measured from center of one nucleus to the center of the other. What's happening to the bond length as our atom is getting larger? It's also getting bigger. And so one of the trends that we explored in Chem 1 was the relationship between bond length and bond strength, and they were inversely related. The longer the bond got, the easier it was to break. And the reason was the further those nuclei got from each other, the less attracted to each other they were ultimately going to be. And so when you have hydrogen fluoride and those two atoms are relatively close together, even though the electronegativity is higher on the fluorine, the fact that they are close enough together that the hydrogen and the fluorine are both attracted to the electrons at least a little bit makes that bond a lot harder to break. But if I have hydrogen and iodine, where they're separated by a lot more physical space, iodine still has a lot of electronegativity, more so than hydrogen does. So the electrons are still being pulled in iodine's direction, but now there's a lot more physical space between those nuclei. It's a lot easier to break that bond because the hydrogen's not close enough to be super attracted. So those are the two primary periodic trends that we can pull. And they really apply the most when we're looking at binary acids, acids where we've got hydrogen and one other atom, and comparing those things directly. But there's one other big trend that we want to look at, and this is called the inductive effect. And again, if you take organic chemistry, you'll hear this term mentioned again. Inductive effect is something that is used for describing how certain kinds of ions and molecules can be stabilized when they gain electrons or lose electrons or have hydrogens move around on them. But here we're going to use it to describe what happens in oxoacids. So oxoacids, again, those are the ones where we've got hydrogen and a polyatomic ion. And that polyatomic ion usually has one or multiple oxygens on it. So the overall trend is this. If I'm starting to compare acids that have similar center atoms, acid strength is generally going to increase with the number of oxygen atoms. So if I'm looking at, say, for example, these four acids here that all have the same center atom and are all monoprotic, I would expect that the order of acidity would start with the fewest oxygens and gradually increase with the number of oxygens. Now the question becomes, well, why? Why is this the case? And so, what is the inductive effect? Well, the way that the inductive effect works is something along this line. Here I have, this is nitric acid, HNO3. This is nitrous acid, HNO2. Structurally speaking, we can see really the only difference between them is that this lone pair here has gone out and grabbed another oxygen atom. And in the process of grabbing that extra oxygen atom, I've got a negative charge on this oxygen and a positive charge on this nitrogen. In nitrous acid, we have none of that. Everything is not only fully octeted, it also is fully formal charge 0. But the thing is, when this acid forms, so the hydrogen goes away and makes H plus, these electrons go in and make another lone pair. The resulting base, the nitrite or excuse me, the nitrate ion has resonance stabilization. That series of bonds is capable of moving around, and that is going to create greater stability in the product. That's a good thing. The more stable the product is, the more likely it is that it's going to go that way in the first place. But the other way that we can look at it is this. If this is the bond that I'm seeking to break, this OH bond, what the inductive effect says is that these oxygens, because of their electronegativity, are going to pull electrons away from the nitrogen, which is going to in turn pull electrons away from here. So all the electrons are going to be moving toward these oxygens here, and that's going to make this bond weaker. So the more oxygens I add, the more capability to pull electrons away from the center I'm going to have, and the weaker that OH bond is going to be as a result. So in nitrite, I have one oxygen that's capable of pulling away, one electron withdrawing group. But with the nitrate, the nitric acid, I have two electron withdrawing groups. More electron withdrawing groups, the more electronegative atoms that I add, the weaker that hydroxide, that OH bond is going to be. And since it breaks at the OH to make an acid, the easier it is to make an acid. Resonance stabilization helps as well, but the inductive effect is describing specifically what is happening to those exterior oxygens. They're pulling electron density away from that OH bond, and in doing so, weakening it. The more that they can weaken it, the easier it is to break. And what we'll see is that when we start looking at carboxylic acids or organic acids, we're going to see similar kinds of effects. The more electron withdrawing groups that we can add, the weaker that OH bond is going to be, and therefore the stronger that acid is going to be as well. And so if I look at, this is kind of the key principle here. The more electronegative atoms there are, the stronger the acid is going to be. And so we can see that all carboxylic acids have this group in common. In fact, that is what is the defining feature of a carboxylic acid, is that linkage there. That's called the carboxylate group. And so if I'm comparing them to each other, I would look at this and say, okay, well, where are the more electron withdrawing groups? Where are the more electronegative atoms? And so from the standpoint of lactic acid here has an additional OH group here. Carbonic acid has an additional OH group there. I would expect those two acids to be stronger than the other two acids because of that electron withdrawing group, which is going to pull density away from that OH bond. In terms of this last bullet point here, the distance from the acidic proton, the closer it is, the more of an effect it's going to have. So carbonic acid, we would expect to have a higher Ka value. We'd expect it to be a stronger acid because that electron withdrawing group is closer to the OH bond that we're trying to break. The lactic acid being an extra carbon away, it is going to have an impact compared to acetic or formic, but because it's a little bit further away, its electron withdrawing power is a little bit lesser than what we would see in the carbonic acid. And if we compare, so if I go to my Ka table here, so let's see here, carbonic is 4.4 times 10 to the negative seventh. Formic, 1.8 times 10 to the negative fourth. Acetic is on the negative fifth scale. And what was the other one? Lactic. Lactic also on the negative fourth scale. Interesting. All right. So apparently forget everything I just said because I guess the explanation for that one would be with carbonic acid, it is symmetrical. So the inductive effects might be canceling each other out there. But otherwise, I mean, we can follow pretty closely along because Everything else, everything else kind of fell in line. But yeah, with the carbonic being times 10 to the negative seventh, that's probably the most likely explanation for it is um, they're both pulling electrons in opposite directions of each other. And so they'd have a negating effect, kind of similar to how we would see polar bonds in opposite directions negate each other in terms of making a polar molecule. I already did that one. All right, so let's do this one together. Based on what we've seen about kind of the periodic trends and inductive effects, what would we determine the following compounds to be in terms of their decreasing acid strength? So decreasing meaning that we're going from largest to smallest. So our first kind of thought here would be that the perbromic and perchloric acids, those are going to be the largest because they have the most electron withdrawing groups. If I'm ranking them based on what we've already seen, the bromine being larger than the chlorine, it would be the stronger of the two. So the perbromic acid would be the greatest, followed by the perchloric acid. And then from there, the bromic, bromous and hypobromous acids would go in order based on their number of oxygens. Since as we are removing oxygens, we are removing those electron withdrawing groups and taking them off there. So based on the trends that we've been given, that would make the most sense. The perbromic and perchloric, again, they should be pretty close. They should both be in the category of strong based on what we've seen, based on what we've talked about. Um, we already know perchloric is strong. For following the trend, we would expect that perbromic would fit in that category as well. And then we would take it from there. All right. I threw this one in here mainly just to see what you would do to it. This is a hotspot question, so click on the proton, the hydrogen, that you believe is the most acidic in this compound, aspirin. So you've got 8 hydrogens to choose from. Which one do you think makes the most sense? So the first thing that you should be looking for here is you should be looking for electronegativity differences. That should be where you're starting the groundwork. So in each of these cases, you see that you've got an OH group here. So that means that the hydrogen's bonded to an oxygen. In all of the other cases here, you've got carbon bonded to hydrogen. Which element's more electronegative, the oxygen or the carbon? It's oxygen. It's oxygen by a lot. Okay. So without any further analysis, you should be choosing that hydrogen right there. Because all the other talk about inductive effects and um, bond sizes and all of that, those are tiebreakers. If we want to look for acidic protons in any molecule, we need to find the proton that's attached to an electronegative element. And then we can start comparing them in those other kinds of ways. All right, so let's go ahead and take a break here. When we come back, we're going to get into the mathematical part of our discussion today and start talking about using ice tables to solve common problems involving acid and base equilibria.